Looks like we're just about ready to get going. Welcome back, folks. And it's official. This is the last day of class. Thanks for making it. Sometimes it's hard to make it to these last days. And if you're coming in through the recording to see it later, totally understand. I was really bad at attending close week as a student myself. Our goal for today is just to do a lot of problems here, reviewing the final exam. I set up a set of problems that are pretty well targeted to the real final exam, mainly to make up for the fact that we closed or canceled a day on, that was Tuesday. This has been a long week. So the final exam review questions here are going to be pretty well targeted to the real exam. And there's a pretty large amount of materials down below to help you prepare as well. So going down the line, these are kind of semi-old materials, but they go all the way up to the last sections that we covered for versions 1, 2, and 3. So this is just like the complete documents. I also uploaded blank exams for exam 1, 2, and 3, as well as one big file for all the quizzes. This is a wonderful source of problems to study for the final exam as well. And if you want to look into the solutions to any one of these exams, just scroll up onto the Moodle site to the relevant exam date, wherever it was for exam 1, 2, and 3, and the solutions are posted for each one of these. One great strategy here is you could just print out one of these exams, start solving it cold, and that will give you some great information on how you're doing on those associated sections. Scrolling down even further, I have the past final exams. Again, this is kind of a makeup for not being here on Tuesday's review, but this was the real final exam given in fall 2024. I listed problems not on the exam, so feel free to skip problems 8, 9, and 10, and solutions are given down below. And same for spring 2024, a year ago. Only problem 13 was going to be omitted on our real exam. Well, any questions at the moment, folks, with the materials? Okay, aside from that, let's take a look into this big block right here. Final exam is kind of hard to specify because this is truly two classes rolled into one, really odd kind of arrangement. Our final exam is also really weird. I've taught at ISU since 2010, and this is the first time I've had a Friday final. Odd, but that's what the registrar wants, so that's what it's going to be scheduled for. It's officially Friday, May 9th. So if you're in the in-person section, that's where I'll be 10 a.m. to noon in this classroom. I've had a lot of requests for earlier exam because Friday is just so unusual. If you want to take an earlier exam and you're in the online section, the exam is open from May 5th, Monday, into Friday, May 9th. So you can schedule your exam for any one of those days. If you're in the in-person section, you'd like to take it a little bit earlier, I'm giving exams on Monday, May 5th, 5:30 to 7:30 p.m. Or if you'd like a Tuesday, Wednesday, or Thursday exam, I can arrange that with Idaho Falls Testing Center. Just let me know and we can make that happen. So far, if you're in the in-person section, you have some options. I'll be here at these times on Friday. If you decide to jump the gun and do it early on Monday, I'll be here 5:30, 7:30 p.m., all in the same classroom. And if you're in the online section, you should have received an email from me saying, I've sent your exam to the Pocatello Testing Center, and all you have to do is call to schedule it. You're welcome to, again, schedule between Monday and Friday, the official time. This is a good point to pause at. Any questions at all, folks, about final exam scheduling? Okay, if any questions come up, if you're watching this video later on, you're not here with us today, and you have some questions, don't hesitate to email me at any point. I'll do my best to clarify. Other things to talk about before we jump into the review is we have several extra credit opportunities starting right here on this one. Some of these have an expiration date. So this extra credit opportunity is going to expire at midnight on Friday. So it's all about getting into WebAssign. Probably what I'm going to do on Monday is just to open up all the sections so all the due dates are eliminated. And you'll have the opportunity to just jump in any section without even requesting an extension. Give me one moment. So that's our first extra credit opportunity, just getting through the homework. And honestly, if you're behind on any one of these sections, that's probably one of the better things to do. You're bolstering up your WebAssign grade and studying for the real final exam all at the same time, since those are real typical questions as well. The other extra credit opportunity with an expiration date is this one right here. This should have been actually posted quite a bit earlier. The math department at IUCU has been really behind. We're overloaded. We're actually understaffed, and that's why we're overloaded. We're trying to hire a bunch of people. This was intended to be posted probably on, I would say, the 14th of April. It finally got posted, I believe, the 28th, Monday of this very week. So this is way behind on this opportunity. And what this one is all about is just giving you an opportunity to evaluate this course. If you click on it, takes you to another link to click on. Let's click on that one. And here's what it's all about. The State Board of Education. So that's my boss's 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 boss. Everybody at ISU has to do exactly as what these folks say. They require that students be allowed. So that's kind of interesting wording. No one's going to force you to do a survey at all, but you have to be allowed to survey this course and give feedback on it. So you can evaluate this course by answering the questions here. On the low end, it could take about 3 minutes. On the higher end, it could take about 15 minutes to go through. Really just depends on how much detail you'd like to give. The results are fully anonymized. And so this is just the way for the math department, the College of Science and Engineering, IUCU, and the State Board of Education, just to see how these classes are going. If you do that evaluation, I don't know why I clicked out of it. If you do that evaluation, answer all the questions, you'll get to a page that says, thank you for submitting your comments, something along those lines. Just take a screenshot or maybe even a cell phone picture, anything like that of that screen, send it to my ISU email address, and I'll add a 4% extra credit to your final exam. That's a lot of extra credit because, Will, I'm asking you to do a lot in a really short time frame. Usually you have a couple weeks to do this. This closes out on the end of the day on Friday. I don't know the specific time, but it's usually in the evening, sometime around 8 p.m. or something like that. So if you miss that opportunity, the math department does not have the ability to reopen it. So give this one a try if you have the extra time. It'll be rewarding as far as the extra credit goes on the final exam. So if you miss any simple mistakes on the final exam, that could cover it up. So I think that's the rundown of the extra credit opportunities. We've mentioned this one quite a lot before, but any questions at all, folks, so far? Yeah.
Yeah, for another class, I wanted to do something like that, but you never heard anything about it. Does it just show up on Google?
It does. Yeah, I have a link right here, and this is really kind of bad in a way. Maybe this is why we're not using Moodle anymore next school year. You have to open a block drawer, and then it shows up right here. And this is not the typical position. Sorry,
For all classes?
Yeah, for all classes. If your department set it up in time, the math department was way behind. So I'm not sure what's going on in, say, like the chemistry department, biology department. But this is a State Board of Education specific requirement, so it's got to be there eventually. Or whoever's the chair of that department's going to get chewed out pretty well, I'd imagine. So it could be here, and it could be at the very bottom when you go to scroll through there.
Okay.
And yeah, there should be a different link for every one of your classes. Kind of annoying in a way to fill out all those surveys at the end. That's one of the reasons I give extra credit, just to help out the department get more responses. Other questions so far? Okay. Another extra credit opportunity that we hinted at is up here in section 5.3. I'm going to ask a problem from this section where we didn't have a lot of time to do a lot of good work on this. But if you study this section, I'm going to ask one problem from it, and it'll be kind of like a problem swap on the real final exam. Solve that problem, and if there's some other problem that maybe you just went blank on, or maybe you just didn't like that problem, you can solve a section 5.3 problem, and the extra credit would be enough to cover it. Your score on the final exam can't exceed 100%. So if you did all problems, then this could just be extra credit to cover up simple mistakes elsewhere. But aside from all that, that's their pretty long set of announcements today, about 10 minutes. We're going to jump into this document here next, final exam review questions. The numbering is kind of funny because I deleted some problems since we were short on time. I wanted to make sure the problems that we solved today are very well targeted to the real exam. But before we start running through these, any questions at all, folks, at the moment? Okay, we'll go down the line on these problems. And if we don't get to every single one of them, I do intend to have them fully solved. So you can come back to this document later on, probably over Friday or Saturday. The full solutions will be posted if you decide to use this as another exam study resource. So let's get started. This is now the work out some limits part of the review. Here we're in chapter 2 using different limit methods. And the major thing we want to look at for every one of these limits is where is x going to? This is the odd one out. When x is going to infinity, it means the methods on this one are quite a bit different from the other ones. And this one is pretty interesting as well because you can't not put 0 in the denominator for that one. So we've got a discontinuity here. X goes to 1, there is no problem on this limit. You can literally, through continuity, just use direct substitution and say this is e to the power of 1 squared minus 1, which is e to the power of 1 minus 1, e power 0 equaling 1. Can't do that on this one because we'll have a number divided by 0, undefined. This one requires more algebra. But watch out for this one. There's going to be a freebie. This is just a property of continuity. Let's see what else we can see here. -5 is not going to work out on this one because that would be 25 minus 25, 0. So it looks like all the other ones are going to require some kind of algebraic method. The method on this one is expand and simplify. So let's go to the numerator. We have a limit as x goes to 0 of expand all that stuff out to get 16 plus 8x plus x squared minus 16 divided by x. So I expanded that out, copied the -16. We have a cancellation going here and here. And that leaves just terms involving only x. So we can factor that out as a next step. It's now limit x going to 0, x leaving 8 plus x behind after factored out, divide by x. And now it's a time to reflect. We were blocked on this problem inputting 0 by direct substitution because of that x. Now that x is gone. We can use direct substitution. We take x equals 0 and just fill it in right there. We have 8 plus 0 equaling 8, and that satisfies the whole problem. So part A, just working through algebra. Part B is tricky since there was no algebra to do, just direct substitution, get a number out. And part C is a little bit more trickier still because this one's all about horizontal asymptotes. That means there's 2 methods to doing this one, really. If you look at this closely enough, you might see that the limit is 2. If you just wrote that on your exam, I'm going to assume you know a lot about rational functions, horizontal asymptotes. That's for full credit right there. But that is kind of vague and confusing. So if you didn't see that, let's show the official method. So the official method on this one is, let's expand the denominator. X goes to infinity of 4u power 5 plus 5. Denominator expanded is going to be 2u power 4. Oh, hang on. I said the limit on this one was going to be 2. Looks like I would have made a mistake on that one. If I put equals 2 on that, might have lost all the credit. So maybe it's a good thing we're expanding this one out. What I thought was the numerator degree 5 was going to match the numerator or the denominator degree, but the denominator is of degree 4 on this one. It looks like this limit is heading off to positive infinity instead. So if you wrote to positive infinity, I'd accept that for full credit, but you know, showing the work on this is probably a good protection just to make sure we didn't miss anything simple. So continue to expand, and it's going to be minus u squared minus 4u squared plus 2. Let's simplify that denominator a little bit. X goes to infinity on 4u power 5 plus 5 over, and down below, two u power 4 minus 5u squared plus 2. Let's get some extra space on that one. Now, the next thing to remark on this is, because the denominator has the highest degree term, u power 4, the prediction, knowing about rational functions, is that this is just a limit of infinity. But this is what the author would do to really show it. We have limit x goes to infinity, and we're going to take that part, divide every single term, numerator, denominator, by u power 4. So if we did that, this would be 2u power 4 over u power 4 minus 5u squared over u power 4 plus 2 over u power 4. Do it again over here. 4u power 5 over u power 4 plus 5 over u power 4. So it kind of explodes in complexity, it appears, when we take that first step. Then we start simplifying. Limit as x goes to infinity of now 4 plus 5 over u power 4 in the numerator. Denominator is going to be 2 minus 5 over u squared plus 2 over u power 4. Next, a theorem about these kind of limits as x goes to infinity tells us that the limit as x goes to infinity of 1 over x to the power p is 0 whenever p is greater than 0. So anything with a positive power is 0 now in the limit. This one will go to 0. This one goes to 0. And this one goes to 0. And looks like I made a mistake right here. Apologize, I'm going to blame this on insomnia. So that should have been upon more careful inspection and cancellation for u. U still survived. But if u's going off to infinity, and there's still just a u right here, this whole thing is now going off to infinity altogether. Again, I should have been able to predict that if I looked closely enough, because the numerator is higher degree than the denominator, which becomes degree power 4 maximum. So that's our method to see it clearly as a limit on infinity. Any questions at all, folks, getting through that one? Okay, let's try out another next. This one is tricky still. It looks like it's going to involve factoring. The denominator is going to go to 0 if x goes to -5, but we can still try to factor this to make some sense out of it. Numerator is a tricky one to factor. Let's do a greatest common factorization first. I write this as limit x goes to -5. First, I'm factoring out a 2 just to make the rest of the factoring easy. If you jumped into factoring right now, it could work out, but a little bit trickier. X squared plus 3x minus 10 is left behind. And the denominator is easy to factor. Just factor out x, leaving behind x plus 5. Then next step is limit x goes to -5 of 2. We're going to factor the numerator in this kind of way. The denominator is x plus 5. And let's look at the ways of splitting this up. X squared will split as x and x. Negative sign here gives us signs in the middle. They must be plus and minus. No other way to arrange this. Factorizations of 10 are like 10 times 1 or 2 times 5 might be a good idea. We put a 5 here and a 2 here. That seems like we're on the right track because that's a cancellation, but we should double check. Here to here is a -2x. Here to here is a positive 5x. The sum of those two terms does result in the middle term. So algebraically, we've got a factorization, and that means we have a cancellation. Those terms are gone. The remaining function, 2 times x minus 2 over x, is continuous at -5. So we just use direct substitution now. The whole result is 2, -5 minus 2, coming from that direct substitution, divided by -5, coming from that direct substitution there. And this is pretty much the result. Numerator is negative 14. Denominator is negative 5. So this simplifies to a 14/5 altogether. I think this one might have been the trickier one, but I made this one trickier on myself by looking at the degree wrong and canceling this part wrong in the first part, getting until we got that right value. But this one's tricky because we don't do a ton of factoring, but we have to be up and ready for that skill as it comes up. It's never going to be anything with a quadratic formula. We're going to keep the factoring kind of light. And sometimes if the factoring seems like it's way out of hand, it might be because we're using the wrong method. For example, sometimes we're doing a concavity problem and we really needed the second derivative. If we're trying to factor the first derivative, we could get just totally stuck. So watch out for those kind of things. The exam is not meant to be a beast on factoring. If the factoring seems really unattainable, there might be just a mistake somewhere. But that's our short review session on limits. Any questions at all, folks, with any of those methods? Okay, after limits, we immediately went into differentiation methods. So this is our good review problem to try out as well. We're on example 3. This comes in 2 parts. And this is kind of interesting because we've sketched a lot of tangent lines in class. We've used it to demonstrate lots of different things. You'll be sketching a tangent line yourself on the real exam. So this just helps you get prepared on this exam problem for when it comes up. We want an equation to the tangent line. Did not specify the method, so we're just going to use differentiation properties to do that. We'll start off by saying, step 1, calculate y prime, or call it dy dx. Actually, let's go with the dy dx. Derivative here is going to be 2/5 x plus 1. So just using the power rule, this term went to a 1, that term goes to a 0 as a constant. Step 2, obtain the slope. And obtain the slope, always use the first coordinate. Even if it's a 1, 1, imagine the one you're using is the first coordinate right there. The slope m is going to be the derivative dy dx because it specifies the slope at all points. We just want the slope when x is 1 itself. That just means we're plugging a 1 right here. So we go 2/5. 1 gets thrown into this position. We have a fraction, slightly annoying, but we'll survive that. So 2/5 plus 5/5 gives us a slope 7/5. That slope in place, we're practically done. Step 3 is just using the ordinary algebraic methods to build the equation of a line with that slope going through that point. Any questions getting through step 2? Okay, we always use the method y minus y1 is slope m times x minus x1. So it's just a big substitution problem. We have the slope at 7/5. We already specified the x1 is 1. The y1 is the other one. Think second coordinate when you think that y1 right there. So this becomes, let's move it to the right, y minus 1 equals slope 7/5 times x minus 1. And that's the equation of the tangent line. You might do a little bit extra algebra on that thing and call this y minus 1 is 7/5 minus, hang on, 7/5 x, that x has to be there. If you made a mistake on the next step, I'm going to look at this step, and if that's a correct equation, I don't think I would dock extra points for any extra work here. Then minus 7/5. So this -1 could be rethought of as -5/5. Y is now 7/5 x. Add 5/5 to both sides. So this is just now a -2/5. But once we have that, all we want to do is just plot that equation. However, when you're plotting these, really it would have been just fine right here because we know this equation must plot in this way. If it's tangent at the point -5, 1, it's going to be the best local linear approximation to the red curve, the original function, nearby -5. So the graph of this line is going to be in spirit, something along these lines. If you draw me something like this, it's absolutely full credit. It looks a little wonky if it came out, say, a little bit like that. That's kind of bad, actually. It looks a little bit weird, something like that. That's full credit too. It doesn't have to be perfect. You could lose points if your tangent line does that. It has to go through the point, right? So this would have been really badly targeted. It's got to be more like this. You could also lose points if it looks like, say, just delete that one. That the tangent line can't cross through that because right around here, they are only matching at one single point, and then they have nothing to do with each other. So as long as it looks like a tangent line, I'm not too worried about you trying to plot this equation perfectly. Let's see if I can control Z back to where it was. Just make it something along those lines, and you'll do great on that problem. Well, that's our tangent line problem. Any questions at all, folks? Okay, that's a good place to start with the chapter since that's what the derivative is attaining for us, the slope to the tangent line specifically. Other things we'd be doing is, let's see, example 4, looks like an application problem. Let me look at what else I've got on here. Yeah, go ahead. Oh, let me take a look at that. Yeah, you're right. I've got a negative slope because it's going down, yet I have a positive slope right here. Thanks for spotting that. Something has gone awry on this problem. Let's see if we can see what could have happened. Yeah.
When you're solving for, you said X to 1 or you said it to 0?
It should be set to the first point right here. So yeah, we plugged in that right point. Let me look at that graph. So this was supposed to be at 1, 1. I think I just messed up this problem. I probably put it together a little too quickly. 1, 1. I've got a point -5, 1. Let's see if we could do some surgery on this problem to fix it right away. Thanks for mentioning that. We'll have to look for consistency as well once we do this kind of problem. So let's open up a plotting tool. The function was 1/5 x squared plus x plus 1. And our point of tangency was supposed to be f at 1. And that's a 2.2. I think I baked this problem a little bit half-baked, it looks like. So this should have been 1, 2.2. That's where our point of tangency should have been. Let's back off this graph right here and put in the correct one. Without a red dot, it just looks ominous. Okay, that looks like a real graph. And now we have other problems, right? Because that's at 1, 2.2. Let's do some surgery on this point as well. That deserves to go into red as a hard edit. Okay, so looks like we do have the right slope. 7/5 is going upwards, but we don't have the right equation any longer because 2.2 now tracks down to this point right here. So that should have been a y minus 2.2. Kind of an annoying problem. I usually try to make a little bit more round numbers on the real exam. Well, let's complete the fix on this one to y equals 7/5 x minus 7/5 plus 2.2. Let's throw that into a calculator now that we have some more awkward numbers to look into. So -7/5 plus 2.2 gives us a 0.8 right here for the intercept. And yeah, that looks like it could be a 0.8. So y equals 7/5 x -7/5 plus 2.2 plus 0.8. And then finally, tangent line should have been like that. Again, thanks for using your logic on that. The tangent line being positive means it should be going upwards. That was a weird problem. I think I threw it together a little too fast this morning. But other questions with that so far? Okay, so again, I guess that's kind of the purpose of having this graph on an exam. Whatever you come up with the equation, think about the slope, think about where the point is going through, and it should all match up. Not quite like what happened on that half-baked problem. This would be the correction to it. This was a real exam problem. It probably would have just been thrown out. Everyone would just be given credit on it because it was definitely flawed on part B. But let's now jump into the next problems. Looks like we're getting into a couple applications. This one's on bacterial growth, section 3.6. After that, this one looks like a section 3.3 problem. And then we'll just do some routine differentiation for extra practice on these. So these shouldn't take too long. We're told here we have a growth problem. And on the exam, it's going to be random, either a growth or an exponential decay kind of problem. So this one says grows at a constant relative growth rate. That information there tells us the model could be specified as P of t equals P at 0 e to the kt. 500 initial bacterial count is telling us that P at 0 equals 500. And so we can plug that right here. Let's just do it right now. Update the model to population at time t is now 500 e to the kt. The next part, right here, let's maybe use this highlighting, is going to give us the k value, the actual growth rate of the problem. It says 39,000 after 4 hours, or P at 4 is 39,000. So let's carry this equation over here to the right column and work out what this is going to give us. What we do next is plug the time of, this was 4 hours, into the model for time t. So we get 500 e to the power k times 4 is 39,000. Now let's do some divisions. 39,000 divided by 500 gives us a nice clean 78. So we have e to the 4k is 78. Take the natural log of both sides, and it's just 4k on the left equals natural log 78. Then divide by 4. K is natural log 78 fourths. Then this whole piece right here just goes into that position. And now we have the full specification of the population size at time t. It's 500 e to the power. I'll put a t times natural log 78 fourths. So this algebra is kind of tricky at first, but give this some practice on some of the other practice exams. Say the exam 3 had a problem pretty similar to this one. Other final exams are posted on the Moodle website, have other versions of this same kind of problem for growth and decay, but it's always this kind of process. Now, next thing we're going to do is just do a couple routine computations. But this is the tricky one, part C, because it's asking for a derivative. So let's just jump to the formula on that one. This is saying, what is the rate of change of the population with respect to time when time is 2 hours? And this is just going to be the growth rate k again times the population size at time 2. So whatever k is, we'll plug in right here. We already have the value. We just need population at size 2. And that's what part B is asking for. So part B is the algebra question. Part C is now the calculus question. So let's plug this in. Population size at 2 hours means we're plugging 2 right up here. And if this is on your exam paper, 500 e to the power 2, natural log 78, divide by 4, then even if you make a mistake in the calculator, I'm going to give full credit just for seeing this expression correct on paper. We still need a number so we can do part C. So let's do our best on the calculator. On this calculator, I would put in 500 e to a power 2, and let me try to stay up there, 2 times natural log 78. Definitely close that parenthesis. That's where the easiest mistake is to make, I'd say. then division by 4. So we should be getting to the nearest cell, 4,415. I'm not going to be too picky on rounding, so if you gave me 4415.88, something like that, you still get full credit. I'll write this as to the nearest cell, 4416 rather. So 4416 bacterial cells. Well, now we're just about done with this. We have the value for P of 2. We'll just plug this here. Any questions so far to this stage? Okay, next step, let's go. It's equal to natural log 78/4 multiplying 4416. And back in the calculator, you use this exact value right here. That's not so bad because all you really want to do is go times whatever that number is, natural log 78/4, and that'd be a fine way to do that kind of problem. Your calculator already has stored, if you're using, say, the TURT TI-30X2S, this information's already there. This is plug in more, and this to one decimal place is 4809.7 cells per hour. I already forgot the number, 4809.7. Cells per hour. Well, I didn't use this value here. I used the more exact value in the calculator. I'm not going to be too picky. If yours looks something like this, I'll assume you did it this way as well. You didn't use the rounded value. You used the exact stored value. But we did, folks. That's going to be either a problem like this or a problem with exponential decay instead. Any questions at all getting through either one of those? Okay, a big takeaway with this kind of problem is when it's a function evaluation like this, it's just telling us the population's size. If we're talking about growth rate, thinking in terms of you're in a car now looking at a speedometer, we're wondering how fast is it growing? And so the evaluation is in terms of cells per hour, much like miles per hour is an analogy. So this is like the speed of growth of the population, but this is just where it is at 2 hours. And those thoughts are really important because not knowing what we have as an output to the derivative makes calculus really vague what we're computing in the first place. Also, this leads directly into question 5. That's what part B is all about. And let's put just a warning on this one. It turns out historically in this class, this is a challenging question on the final exam. So let's emphasize that just for the extra help on it. This really is on the final exam, and this is a challenging final exam question. Our A is not too bad though. We're getting pretty good at calculating derivatives because we've done hundreds of them at this point. But this has context. M is body mass in grams of a laboratory, hang on, rat. Let me fix that typo there. This is supposed to be a kind of a biology kind of problem. Let's start over. The body mass in grams of a laboratory rat after T weeks is modeled by the function M defined in this way. So some quadratic function. And this is just for the first 10 weeks of its life. So we want to calculate M prime at 4. 4 is now saying 4 weeks. First thing we do is just calculate M prime at T. We want the actual derivative, then we plug in the value. So the derivative at T is going to give us 0 on this term, 45 on this term, minus 3 times T on this term. And you know what? Even though, oh, hang on, no, it does ask for units. Let's throw in the units right here. It's a good idea. If I don't have that on the real final exam, still a good idea because it's going to help us a lot in part B. This right here is going to be in units of M first, grams per whatever the unit is for the variable t, and that unit was weeks. So it's 45 minus 3t grams per week. We want m prime at 4, so we go m prime at input 4 weeks is 45 minus 12, so 33 grams per week. Any questions about that so far? Okay, so now the interpretation on this one. Again, this is a really, really polarizing question on the real final exam. Either people had it perfectly or they were off base on this one. And the easiest way to be off base is to say m prime at 4 is this, the grams at 4 weeks. But that's not what it is at all. It's something more like this. We have to roll into it the fact that it's a derivative. It's a rate of growth. So come down here and say something along the lines. We have to use the context, the fact that it's about rats. We'll say at week 4 of the rat's life, we're looking into its body mass. I'll just say mass for short. Its mass is increasing because of the positive quantity here at a rate of 33 grams per week. So the key elements that we have to make sure are present here are that we're talking about at week 4, because change the value here and the growth rate will absolutely change. We plugged in 10. This is a pretty large juvenile rat at this point. So its growth rate should be smaller. It would be just 15 grams per week at week 10. So we have to have that information in somewhere. Here, we're just talking about the context. You have to either say increasing or decreasing, but we're just matching whatever sign we see here. Positive means increasing, negative would mean decreasing. And we have to have the fact that it's a rate and the units as well. So lots of required elements there, making it, again, a challenging problem. So it's a good one to give a heads up to as well. Any questions at all, folks? Finalizing this one. Okay, so that's a couple application problems. I would say this one is pretty much a guaranteed problem on the final exam, but the context would change. It's going to be something highly similar, however. Another block of problems on the final exam looks like this right here. Just ordinary differentiation problems. So let's give this a try. It's been a little while since we ran through these kind of questions. The derivative here is not ready to just launch into, unless you're really good at the power rule when the base is in the denominator. For me personally, I'd reformat it. F of x is, on this term, make it negative 3, x power negative 4. This term is fine as is. Looks like the rest of them are. 9 natural log x minus 5 power of x plus natural log 6. Other thing to be aware of as you're studying for the final exam is that there will be some formulas for this kind of stuff, but there are certain formulas we do have to have memorized. Take a look into this formula sheet right here, and this will tell you what formulas we have, lots of limit laws, lots of differentiation properties, properties of logarithms. As far as the differential formulas go, we do have to be familiar on how do these certain derivatives work. So one formula is going to be for this one right here. The derivative with respect to x of natural log x, we have to know is 1 over x. And I'm not sure if I'm going to actually put one like this on the final exam because this is not one we've done a lot of. But the derivative with respect to x of something like that, 5 power of x, is going to be 5 power of x times natural log 5. And this one's a constant, so its derivative would go to a 0. And just for the sake of completeness, the big formula on that one is derivative with respect to x of x power of n is n times x power n minus 1. But that's our power rule. We've probably used it a few hundred times at minimum so far in class. This one gets used a lot. So now we're ready to go on this. The derivative, f prime at x, is going to be First, the power rule, -4 comes down and multiplies. So this is a 12. X to the power. And this gets vague after antiderivatives. Does this go up or down? Anyone recall the direction? Yeah, it goes down, so larger negative. Yeah, kind of confusing. So differentiation, subtract one. Into anti-differentiation, go up by one, add one. So -5 on that one. Here, it's a constant multiple rule again. This will be just plus 9 times 1 over x, or 9 over x is a great way to write it. This one's going to be -5. X to the power natural log 5, based on this formula here in the middle. And this one's a constant, so it goes to 0. Since there's no x here whatsoever, this is a constant and goes to 0. So that derivative's done. On to the next one. Looks like they're getting a little bit more built up as we go. Here's where the exam does have some extra help on the formula sheet. We're going to be using these formulas here for product rule, quotient rule in the next couple. We also have information on basic exponential, power rule, and that kind of stuff. So first on this one, we've done a good amount of product rules, but this is a review, so let's not try to race through this one. G prime of x on this problem is going to be first the derivative of this part right here. When we differentiate that, we're going to get, let's see, 30, 24. So it looks like 54 x power squared. Then we copy in e to the x. Then go plus, copy in 18x cubed. Differentiate the e to the x through the power rule, and it becomes just itself, e power x. Then at this stage it's done. All we had to do is follow the power rule in that kind of order, where you differentiate, copy the second one, copy the first one, differentiate the second term. Any questions at all, folks, with that one there? Okay, let's take a look into next one. Now we're getting into quotient rule in part C, but really it's the same kind of idea, just a slightly different schematic for how it comes together. So this time we'll organize as numerator versus denominator. Hang on, this one looks a little bit more challenging upon closer inspection. The variable is v, which just looks weird, but there's also a chain rule there. Let's maybe work that off to the side. That's a pretty good strategy on the exam. Let's simplify by just handling this derivative all on its own. E to the power of 5v prime. The format for this is e to the power 5v times the derivative of 5v. So that's the pattern we wrote out each and every time. Does that look right to folks so far? Okay, there's one last derivative. This is like taking the derivative of 5x. Even if it's v, we just get a 5. So this is 5 e to the power 5v. And we'll just use that over here once that portion comes up. So now the derivative is y prime. And here's the pattern on this one. Much like we differentiated the first factor and just threw it in, here we'll differentiate the numerator. It's linear, so this is just at 5. Then we copy the denominator, e power 5v. One big change is from plus, we go to negative in the quotient rule. Then copy in the numerator, unchanged, 5e minus 3. Multiply it by the derivative of the denominator, which we pre-computed over here just for ease of computation, 5e power 5b. Then the denominator squared is what we'll put in this position. Denominator is e power 5e. And if you left it in this format, I wouldn't be too opposed to that because it is a timed exam and you did compute the whole derivative. But in case we're doing something more involved, we do know that sometimes we do have to simplify these. Let's just take the extra practice and time on this one to simplify as well. You know, a good simplification here is e power 5v appears in this location, and down here to power 2. Best way to simplify is actually to factor, not expand. So we'll go and write in e power 5v factored out of the numerator is going to leave 5 minus this term. Let's distribute the negative as well, minus 5v plus 3. And let me make sure I've got, oh, hang on, didn't quite get it all. Let me try again. Let's take our time with that one. We'll factor out e to the power 5v, 5's coming down. E to the power 5v here is eliminated, but I still have 5v minus 3. That 5 is going to have to distribute through. Does that look right to folks so far? Then down below, e power 5v squared. Yeah. Yeah, that would have been a good call, actually. That way, less algebra to work out right here in the middle. Let's backtrack and make that step happen. Also, I think it makes us more accurate since that's an easy one to misconfigure if we forgot it was there. So factor out the greatest common factor is the best advice for this kind of problem. Leaves just a 1 here, so we're simplifying as we go as well, a lot more. And leaves just 5v minus 3 negated. Let's distribute the negative now. Negative 5v plus 3. And now this is way easier to simplify in this format. Here's what the cancellation would look like. E power 5v is gone from here. This is e power 5v times e power 5v. So the power's gone. It's just power 1 now. This leaves behind 5 times. This is 4 minus 5v. Divide by e power 5v now to power 1 after that cancellation here to here. And if we had to set this equal to 0 and solve, get critical numbers, we're in the right format to do that kind of work. But here, all we're doing is differentiating, so the step ends right there. Any other questions at all, folks? Getting through the algebra on that one? Okay, next one is a callback to properties of logarithms like we saw on exam 3. There's going to be a problem like this one, a little bit less involved though, on the real final exam. So probably what you want to cite then is this portion is going to be here, properties of logarithms. Let's throw it on the exam as a reminder. And it is a tough problem because this is one of those problems where algebra is a prerequisite, but logarithms tend to be covered usually pretty late in an algebra class, right around probably weeks 13, 14, 15. Sometimes it's really hard to absorb this kind of material. So this is our chance to bring it back. It's part of the course and see how these things go in another kind of context. First thing we're going to do is start expanding this function as much as possible, then we'll differentiate. So h at t, no derivative just yet, is first, use the quotient rule right here. We're going to split across that fraction bar and write in natural log x e to the power 10x minus natural log. And instead of writing in the square root, let's also simplify and write it as 2x minus 11 power 1/2. So that takes care of the first portion. We've split up the fraction. Second portion, we're going to split up the product on this one right here. So now it's natural log x, we use the plus, then natural log e to the power 10x. And we can use a property on this one right away if we'd like. That's property number 7, which tells us the power 1/2 can now become a coefficient. So this 1/2 goes negative 1/2, natural log 2x minus 11. There's no property for a difference inside logarithms, so this one's done. But we still want to take care of that 10 power x. That power comes down, is going to simplify life a whole bunch as well. So it's natural log 10 plus 10x coming down, natural log e minus 1/2 natural log 2x minus 11. Final thing, I think this property is probably the hardest one to see. The natural logarithm of e is just a 1, and it's through, let me fix that, highlighting there. through this property right here. If we rewrote that in terms of base C, we'd say log base C, but the shorthand of that is just natural log. So if we put in the base, it'd be E, power of X, tells us cancellation here just gives us X. Now, if one more thing, it was just like that, you could put a 1 there. This is going to work for all real numbers X, and then you would just get 1 as a result. That tells us the cancellation here just leaves a 1. So if it's a 1 times 10x, all we've got left over is 10x. So the thing we really want to differentiate, which I promise you saves a lot of time to get the accurate derivative, is natural log 10 plus 10x minus 1/2 natural log 2x minus 11. So that's phase 1 on this kind of problem. This will be one of those problems where there's lots of space to write out this kind of work. Phase 2 is just to differentiate whatever's on this line. Any questions first with the properties of logarithms? Yeah. Other questions at the moment? Okay, let's run this through. The derivative h at t is, we still want to go carefully, but this one's not so bad. Let's just recite the formula. Apply a nice formula. We just have to be ready for it. The derivative of natural log x, just a 1 over x. So this one is done, 1 over x. Now, if we left it in this format, that would have been a tougher derivative. It would have been a chain rule with 1, 2, 3 functions. That's kind of a mess. But we use properties of logarithms, and now it's a 10x. That derivative is 10. Huge reduction in complexity on that one. Then over here, it's the constant multiple rule. Negative 1/2 times result of this derivative here. That one's a chain rule. And just for the sake of a review, let's take our time this time on this chain rule. The inner function is 2x minus 11. The outer function is the natural log x. So when we go to differentiate this one right here, we use that process. It's going to be 1 over something that we multiply by the derivative of that something. I think we often use green for the inner function. So let's do a call back to that. 2x minus 11 goes here. If this was just natural log x, we would have done this, but now we threw in 2x minus 11, the same exact input. 2x minus 11 will also go here. And now it's just one more derivative to finalize. Because it's multiplying into a fraction, this just goes up into the numerator here. So we have 1 over x plus 10 minus 1/2 times 2x minus 11. This derivative is 2. So that work is done. That also gives us a cancellation here to here, leaving a 1. And so our simplified answer is 1 over x plus 10 minus 1 over 2x minus 11. And you don't have to do anything further. There's no need to combine like terms, find least common denominators, any of that kind of work. This would be just fine as formatted. Well, that's the full view on this problem right here. It is a challenging problem, but use properties of logarithms, and this is going to be a lot of credit just to get it down to here. So if you get to this point, you're going to be in great shape for the derivative below. Any other questions at all, folks, with this one? Yeah.
Could you show something to the derivative of x over natural log x?
Yeah, absolutely. That's a kind of a tricky one. So let's go y equals x over natural log x. This one's tricky because now we're hitting this one with quotient rule altogether. So the quotient rule setup will be x over natural log x like that. dy dx. Let's do this one carefully as well, just to see the full format. We'll differentiate the numerator, so x prime, copy the denominator, natural log x, go minus in the middle for quotient rule. Then copy the numerator, x, multiply by the derivative of the denominator, so natural log x prime, and divide by denominator squared. So that's going to be our setup on quotient rule. This derivative is not too bad. That'll turn into just a 1. Let me write it in just to show we didn't forget about it. There's that 1 from the derivative. Then minus x times, and this is where something kind of interesting happens. This derivative turns into a 1 over x. Let me kind of reformat my fraction bar here. And that means we get a cancellation right in this spot. This will turn into a -1. Divide by, I'll just write that in as natural log x squared that way. So simplifying as we go, this is natural log x. Here, negative x times 1 over x is just now a -1 after canceling over natural log x squared. So kind of a tricky one to get set up and get going. But once you get to this spot, just kind of follow your nose on each of these derivatives and run it through algebraically. Does that make sense on that one there?
You can't do like x times natural log x -1, right? You can't bring it to the top.
This part right here.
Oh, no, I'm sorry, just so x over natural log x.
Oh, I gotcha.
You can't just bring that up, and
You actually can, absolutely. So if you decide to go that route, you would write it as y equals x. This part can come up as natural log x power -1 in that format. And this derivative works too. It's kind of an exchange. You're exchanging out a quotient rule for now a product rule, but together with a chain rule as well at the same time. I think it's a slightly tougher one just because the chain rule in that spot there. But you would get the exact same kind of answer. It might look a little bit different formatted. Should we give it a try just for the sake of it? All right, let's give this one a try next. Sometimes that is a good exchange. If the quotient rule just looks unsavory and you don't mind another chain rule baked into the problem, it is a good way to go. Let's compare the formats as well, because it does look interesting when you do it this way. So product rule would be derivative of that times the derivative of that portion. So dy dx this time is going to be derivative of the x, so just a 1 there. Then copy in natural log x power -1, and then go plus. Now watch the formats because they really do look different, but they come out just the same. So we'll copy in the x. Now this is a tricky derivative because it is a chain rule. Let's do the strategy of work it out in the margin. So it's natural log x power -1. In our chain rule analysis on this, we would call that function 2, inner. And the power -1 function is function 1, outer. So now if we rewrite this as natural log x power -1 prime, so we're differentiating that whole block right there. First thing we do is the outer derivative. So this will be negative natural log x, power goes down by 1, so now it's -2, multiply by the derivative of natural log x. This is a good spot to pause right here. Does that make sense on the chain rule run through? Awesome. So we'll get negative natural log x power -2 times this derivative here is just now 1 over x. And yeah, that looks kind of strange algebraically, but let's just import it directly up to here. Derivative of all that became, I need a bracket because we're multiplying and there's a negative sign. We can't accidentally convey subtraction. Then natural log x power -2 times 1 over x. We still get a cancellation here to here, so that part's gone. And what's surviving is natural log x power -1 minus natural log x power -2. Looks like we've got all there. Now, how do they compare? Because they look way different, right? We can fix the exponent on this one if we chose to, but if you took this process and left it in that form, I would give full credit to that format. But this is a 1 over natural log x. All I've done is taken the base, drop it to the denominator. That's a minus 1 over natural log x squared. And then the comparison with the one above is, this is fine just in that format, but you could divide natural log x squared into both. It would be natural log x squared minus 1 over natural log x squared like that. Then there's a cancellation here to here, giving us 1 over natural log x minus 1 over natural log x, almost got it in there, squared. So the formats match up, but you'd have to take an extra step here to really see it. I'd say this is a pretty good way to go, but you'd have to be comfortable with that chain rule right here to really make it work. Other questions so far with that one? Or any other ones as well? Always open to suggestions for these kind of reviews. Okay, we've got about 10 more minutes, well, 9 more minutes so far. So let's cherry pick on the next problem. This is an optimization problem with no context, local max, local minimum. This is an optimization problem with context. So it looks like another antibiotic drug concentration type of problem. Slightly different sort of function, but nothing too different than what we've done. Then after that is antiderivatives, and this would be the extra credit type of question on the real final exam. Any questions that folks would like to see first out of that list? Let's give it a try. So example 9, that's a good call. This is our optimization problem. And when you're preparing on the real final exam, I'm not going to go too out of the line on this one. Take a look at how you did on your quiz, how you did on exam 3. It's going to be pretty similar. This one is a little bit tougher, but good for the sake of practice. Here's step 1. We've got to differentiate this function. It's in a weird format. It almost would suggest you're using a product rule, but you're not. That's a constant multiplying something else. It's really the constant multiple rule. Challenge here is the chain rule portions on this part and this part. So let's use the strategy of work it out in the margin first, bring our results together. You have to differentiate that function, e power negative 0.2 t prime. Derivative of it goes like this, e power negative 0.2 t times negative 0.2 t prime. So all it is itself, e power negative 0.2 t, multiplying by the derivative of the exponent, that's just a negative 0.2. Similar token, let's differentiate that part, e to the power negative 0.6 t prime. But let's use the format that we're observing. Each time we differentiate an exponential, you get the same exact exponential in the same exact format. Then you multiply by the derivative of whatever the exponent is. This one is now negative 0.6. So that's the derivative of each one of those terms, just for the sake of putting them down. Now the real derivative we want, c prime at t, is going to look like this. Constant multiple rule says nothing happens to the 8 because it's multiplying. Then this derivative we worked out to get that. So negative 0.2 e negative 0.2 t. There's a minus in the middle. And then this derivative gave us another negative sign. Solve this right here. So let's put in minus 0.6 e to the negative 0.6 t written in like that. So we've got our derivative. It's kind of tough to say which one's harder, the ones we did on exam 3 or the quiz problem, because the exam 3 and the quiz problem had a product rule. This one just had 2 chain rules, so it's equivalent difficulty, slightly different kind of format in the function. Let's do the good important work of simplifying it as much as possible. This is 8 times negative 0.2 e negative 0.2 t plus 0.6 e to the negative 0.6 t. Might as well distribute 8 through. This is negative 1.6 e to the negative 0.2t plus 6 times 8 is 48. That's a 0.6, so 4.8 e to the negative 0.6t. The next step is, if we're using the first derivative test, we want a critical number next. Well, we did all the hard work really to get to the critical number. This is the derivative in possibly its most simplified form. Set equal to 0 now. Equation solving on this one's a little bit different. What I would do this time is add negative 1.6 e to negative 0.2t to both sides. So 4.8 e negative 0.6t is 1.6 e to the power of negative 0.2t. Now let's think about this one. One way to solve this is to get the exponential on both sides. And that's pretty doable. Let's just eliminate it from this side. You can multiply this side by e to the power positive 0.2t. This forces you to multiply by the same thing on this side. The reason that's a good choice is when this multiplies, the exponents add up. That's negative 0.2t plus positive 0.2t. It's just e power 0. It's a clean cancellation. So on the right-hand side, just a 1.6. This would cancel. On the left-hand side, no cancellation. A little bit more complicated. We have 4.8 e to the power. These exponents add together when we multiply those two base C exponentials. Let's do it on the left just for the sake of clarity. E to the 0.2t multiplied e to the negative 0.6t is e to the power of negative 0.6t plus 0.2t. So we get e power of negative 0.4t. That's our new exponent. E power negative 0.4t. Well, what can we do with this? Let's just divide 4.8. Why not? Let's isolate the exponent, trying to look like an exponential decay kind of problem. To solve for t, we want to eventually take the natural log, so clear out the 4.8. So let's go 1.6 divide by 4.8. Looks like it's 0.3 repeating. That's 1/3 exactly then, if it really is repeating. I'm going to write it in as a 1/3. E to the negative 0.4t equals 1/3. Take the natural logarithm of both sides now. Negative 0.4t is natural log 1/3. Taking the natural log of the left, cancel the base e exponential. Now divide by negative 0.4, and t is natural log 1/3 divide by negative 0.4. Let's get a number out. That's our critical number. And just to check out how people are doing in Zoom, I have something that says preparing live stream. Everything working out so far? No lost connection, video feed, or anything like that? Sounds like we're probably okay. Let's hope for the best. Well, after doing the division, putting into a calculator, see where we're rounding to. Didn't say, so let's use our best judgment. I'd go for 2 decimal places. And I forgot the time value. Awesome, thanks for letting me know, Kate. Always weird when the technology gives me strange messages. And this was in hours. So we'll say that in hours, it is 2.75 hours. So that's our critical number. To finalize the first derivative test, we go like this. 0 hours is the time of injection or consumption. This is t hours, and we have a critical number, 2.75 hours. What we need to do is check out what is the sign of the derivative on that interval right here, and on this interval. We use test values. A good test value here could be 0. 0 is in this domain. That's the point where we injected the antibiotic. And this to power 0, let's see, that would give us C prime at 0 is 8 times. A 0 here is a 1, so that's just a negative 0.2, plus 0 here is a 1 as well, so that's a positive 0.6. It's positive right inside here, so greater than 0. And that would tell us greater than 0 here. Concentration of the antibiotic is increasing. We just want to check, is it decreasing out here? 3 should be a good value to check. So let's do 3 C prime at 3. And it's kind of an awkward function to throw in a value 3 in. So this is a point at which we'd want a calculator. Go 8 times negative 0.2 e to the power. Plugging 3 there is a negative 0.6 plus 0.6 e to the power. 3 there is a negative 1.8. And hey, we get negative. That's what we're wanting to show. So I'll also just say here, C prime at 3, we used a calculator, and we did find a negative value. I'll just write down less than 0. That means the derivative is less than 0 here, we're decreasing. And then it allows us to conclude, therefore, we have absolute max concentration at 2.75 hours. This one's a pretty non-standard one to get through. We didn't do a lot like this one. So think of this problem here as pretty good practice. I'm gonna, again, when I write down a problem like this one, because they are challenging, it's gonna be pretty similar to the quiz problem and the exam 3 problem as well. So take a look into those for extra practice. And sometimes it is a good idea to do harder problems like this one, just for further practice. But any last questions at all, folks? Concluding this review. Okay, we left a couple problems still on this document. So starting on Friday, I'm going to start working on solving all of these, posting the total solutions. And last piece of advice as we're reading for the exam, I do have office hours on, let me see here. Where'd it go? I have office hours on Friday. I'm going to be available by Zoom from 1 p.m. to 2 p.m. And our final exam is officially on Friday. I don't have any office hours next week, but if you want to connect, work on some stuff, either email, and we can make something work out. I'll be very happy to work something out with you on Zoom for extra practice. Otherwise, have a great time studying. Good luck on your other exams. I'm not going to try to make this exam too wild, and it is the one exam that I do curve on the rest of the semester. So study like you've been doing on the rest of your exams, and you'll be in great shape. Well, take care, folks. Have a great weekend, and I'll see you later on. Sorry, say again? We do not, no. Yeah, so no official classes on finals week.
I have a question.
Yeah, go.
For the review on Friday, is that just on the same Zoom link that's on Moodle or?
Yeah, that's correct.
Okay.
Just the same. It'll be like a class that just got moved over to Friday instead of our usual Tuesday.
Okay, and that's like tomorrow?
It'll be tomorrow, yes.
Okay, perfect. Thank you.
You betcha. I forgot it was tomorrow. Thanks for reminding me as well.
So no classes for any classes next week?
That's correct. Yeah, it's just the final exam schedule now. That's kind of weird. We say it's a 16-week semester, but it's sort of a lie. It's really 15 weeks and then an exam schedule. See you later.